All right, here we go. Physics reaction video number 41. Let's get started. Oops. Get rid of something here. Sorry. There we go.
Our chapter on energy, I know I mentioned it a little yesterday, but we're going to talk more about defining what work is, and that'll kind of take us into energy.
Cool.
But before we get there, we need to start talking about work and how that is associated with energy. So we know energy is the ability to do work. So we have energy, we have the ability to do work, which means we have the ability to produce a force that is capable of acting over a distance. But yet, I still had.
All right, let's break this down. Energy is the ability to do work. So if I've got gravitational potential energy, it means if I let it go, it can fall, but that means the gravity will do work on it. Okay, I like that. What about thermal energy? Yeah, I mean, there's, the efficiency in a thermal engine is this problem, right? Where it's like, you might have all of this thermal energy, but be careful trying to extract it all. Or if you want to do it cyclically, you're going to have problems. And then it says, any object that has energy has the ability to create a force. Certainly that's true with thermal energy, gravitational energy, nuclear energy, I guess. Yeah, okay, I can live with that. All right, cool.
And really help us define work. And so we know this idea, there's this combination of energy and work, and they're kind of the same thing. Let's try to define it a little bit further.
Love it.
And so when we talk about work, work is the product of the force on an object and the distance through which the object travels. So
I talked about this yesterday. The work energy theorem versus the impulse momentum theorem, right? Which one makes more sense to students? If you push on something, what do you think matters more? Pushing it, how far you push it, like how long of a distance you push it, or how long you push it in time? I don't know. I feel like the time one feels, maybe it's just our culture or something, like how long did you stick at it? Really keep on pushing, as opposed to I've made it this far. So I've always wondered about this definition being something you can internalize. Certainly it's a definition you can run with. In my work where I've tried to show that really momentum is the only thing that matters and energy is just an accounting trick. Really what he's going to go through today is the accounting trick, I'm guessing, right? The work energy theorem is an accounting trick, keeping track of where all the momentum goes. Not everyone agrees with me. Let me turn on the light so I don't look so dark. So I think that he even said it, right? He was like, well, boy, it said work, and energy are these related things, but we're going to have to understand exactly what they're doing. And then, so let's back up a little bit.
Object and the distance through which the object travels. So what that means is whenever we're applying a force and an object moves, work is going to be done. So we can simplify that into work equals force times distance. And so when we apply this force, the object is going to move in the same direction as that force applied. All right. And so the amount of energy needed to move something is also known as work. This is another way of defining it. How much energy is needed to move a water bottle, to pick up a box. That is work. Work is just applying a force over a distance. So if an object doesn't move, then no work is done. So what does that mean? If you take this full analogy and you were to hold it up, you can take an object, any object you've got, you were to hold a heavy object and it not move at all. You may feel that your muscles are working, but you're actually not doing any work at all.
Just going to pause right there. I have really struggled with exactly what he just mentioned about the muscles feeling tired. I don't know. I talk to biologists about how muscle works, how muscles work, and I find it's a struggle because let's compare and contrast two things. So my big old 64. I just put water in this, by the way. It just lasts a long time. Turns out during COVID, all the water fountains are blocked off, so I have to go a really long way to get water. So turns out 64 ounces lasts a while. Anyway, so if I just hold this and don't quote unquote move it, I do get tired. I get tired, eventually I got to put it down. And what he's saying is we're not doing work as defined on this screen. But a really interesting question is, what if you made a mold of me, some sort of robot version of me, and you clamped this joint, and you clamped the elbow joint, and you clamped the wrist joint? Will that also eventually wear out the metal, right? And so usually the answers have to do with like twitch fibers and things like that in the muscles, like microscopically you're holding and they're slipping and they're slipping and they're slipping, and then you have to refire to sort of re-energize them again. And that's why you get tired. But this idea that just holding something out there, as long as you don't move it, you're not doing work. I think he's hit it on the head, that we have to be careful with this definition, because just getting tired doesn't mean that you've done work as defined on this screen. So I'd love to hear how you guys deal with that. What are some really good ways to handle the relationships between being tired and doing work as defined here?
Is we have to have some type of distance being moved. The net force is 0, and so we're not actually applying a force, therefore we're not actually doing work, and it's not covering a distance. So in order for an object to do work, we must have it move, okay? And so we get into this formula where force or work equals force times distance. This is more specifically net force, because we know force is a vector quantity where things work in opposite directions. And so whenever we have a net force acting on an object and the object moves a distance, we can help define work. Remember
So it's interesting. It seems like physicists ran out of symbols, right? So this surely looks like multiply to the students. To many of us, it looks like a cross product, right? And well, maybe you would say these are bolded and that these are all the vectors. But that's not right. Force crossed into distance is not correct, right? It's just force dotted into distance. And so it's so interesting that we start to recycle some symbols. Let's see, in a class like this, they're going to see a cross product, maybe in torque, which is probably the next section. And so suddenly we suddenly say that there's this symbol that means something completely different. For dot products, we literally put a dot here, and I think students are starting to be okay with dot as multiplier. Some of them just like a space as multiplier. In Mathematica, for example, space means multiply. And it makes things look nice, but it actually can get you into trouble if you don't actually use like the asterisk sign in say something like Mathematica. Because vector scalar, this can't be a cross product. It has to, we know that it ultimately is a dot product. The dot product is interesting because it sort of captures what he was saying in the previous slide about must be in the same direction. But it's tough. And so sometimes we just say, we don't use the concept of dot product. We just say, oh, well, just figure out whether it's pushing in the same direction or not, or get the component that's moving in that direction. Well, that's what dot products are great at, but it depends whether you really want to embrace that and run with it. I'm guessing, based on some of the things that he's doing, he probably wouldn't do the dot product here, but let's keep watching.
It works also the ability to move this object, or the amount of energy needed to move this object. So we measure work in joules. Notice the spelling right here. So joule is the same way we measure energy. And so 1 joule is equal to 1 Newton times a meter. So it's a new unit.
Well, here's the dot right there.
When we say joules, we're talking about energy and work. And so newtons is how we measure force. Meters is how we measure distance. And so the SI unit is going to be a joule. So if there's no net force acting on an object, no work is being done. If there's no distance, the object moves, no work is being done. All right. Cool. So hopefully you understand this connection between no movement, no work. Okay. And so we're going to get to an example problem, and then I've got 4 for y'all to work through. So weightlifters and bench pressing a barbell, his weight is 710 Newton.
So 710 Newtons means about 70 kilograms, which means about 150 or so pounds. So that's a lot. So let's pretend he's teaching high school students. The number of high school students who can bench over 100 pounds is not many, I would guess. It's a moment, right, where you could do this kind of calculation. Students could just churn this stuff out and not think about it, but he's got people in his class that can bench press 150 pounds, because these people exist. I don't think I'm one of them. So it's interesting also to realize that the world record is 700 pounds-ish. I'm not 100% sure. Let me find out. Hey, Google, what's the world record for bench press?
350 kilograms, 770 pounds. According to Top 10 Sports,
770 pounds.
raw bench press.
So it's interesting that this is actually pretty dang close to the world record. And by the way, this video is only about a week old, so this isn't an old video of his. So it's interesting that this is, if this were reinterpreted as pounds, it would be near the world record. As newtons, it ends up being whatever it is, a fifth of the world record. So that's really, really interesting. All right, let's keep going. Oh, and by the way, notice this. This is fascinating. I can't wait to see what happens there.
He raises and lowers the barbell at 0.65 meters at a constant velocity. How much work is done raising the barbell?
We don't care about this part.
When an object is moving at a constant velocity, right, we know it's not accelerating. And so the force, the weight that we're overcoming when lifting this up is just the weight of gravity.
Good point.
Right?
Good point.
Force downward. So in order to make this barbell go up with a constant velocity, we're also applying a force of 710 newtons in its head.
Well, that was great. So my first reaction was, who cares? Who cares? All that matters is distance. All we needed was the force and the distance. And I had in my head, this is going to be the force. This is going to be the distance. And I really loved what he did because I got caught up short, right? The constant velocity is super, super important because he's saying there's no acceleration getting done. So you're just barely giving it enough force to overcome gravity, which means that your upward force is going to be 710 newtons. And I just wasn't thinking. I was jumping ahead. So that was really great.
Heading up, right? And so we're going now a distance of 0.65 meters. So that means that we must be covering a distance. Therefore, we're doing work. And so work is force times distance. We're doing 710 newtons times 0.65 meters. And if you plug that into your calculator, you're going to get 461.5 joules.
So I was sitting here thinking, how to internalize energy measurements to think about whether it's a lot or not. And so I was thinking, 461 and a half joules. Sorry. I was thinking, I should figure out, the equivalent of how much that would be lifting something. So, hey, it turns out that's exactly equivalent to lifting a 710 Newton thing, 0.65 meters. So, I say that because I don't think many of us have internalized energy. Frankly, I think I've internalized microscopic energy a little bit more. I sort of remember the rest mass of electrons better than I can remember things in the macroscopic universe. So another question for you guys is, how do you help students sort of get a sense of energy numbers? Now, this next section, let's make some predictions here. He said, what about lowering it? Well, typically when you lower it, you also lower it at a constant velocity. In fact, it says that both is being done. So the amount of force that the weightlifter is providing is the same, both up and down. The distance is going to be the same. So you might get this exact same number, but it's going to be negative, right? And so I don't know how it's going to end, but let's talk about this. The total work done on the bench, on the barbell, is going to be 0, right? Because this is going to be positive 461 and a half. This one's going to be negative 461 and a half. The total work done, let me say this and you can yell at me, the energy passed on to the barbell is going to be 0. And yet we know you get tired doing this, right? And so again, this idea of tired versus work. So let's see how he handles that.
Because a Newton times meter is a joule, right? And so what happens if we're lowering it? How much work do you think we're going to do when we're lowering it? Again, at a constant velocity. It's going to be the same amount, just negative, right? Because we know force is a vector quantity, so direction matters. And then work would now also be a vector quantity. So if we're doing work downward, we know that's negative, right? Or if it's against the motion, we're going to have it negative. And so we've got negative 461.5 joules.
So he said work was a vector quantity, and I know some of you just freaked out when he said that, but all he's really talking about is that for this calculation, direction matters, right? For this calculation, direction matters, and so we end up getting this negative sign. Love it. So I'm just going to back up a little bit and again look to see if he talks about the sum or not.
We've got negative 461.5 joules, right? Okay, So look at this dumbbell. This guy right here, or barbell, has lifted it over his head. And so let's imagine at this moment right here. So we know he's done work to get it up here. Now what? Is he doing work as he holds that object or that barbell stationary?
Love it.
Well, the work's done lifting it because we've covered a distance from the ground up. But as he holds it over his head, no work is being done. The net force is zero. We're
So
countering the
tough.
force of gravity with a force upwards, and it's not traveling a distance. And
Yeah, I mean, so I'm pausing just to, right. This is really, really tough because you can imagine the students who are like, I've done this. That sucks. I hate that part. Right. You look at this guy's face, doesn't look happy. Right. So I think that we have this struggle between sort of microscopic muscular energy transfer and macroscopic definition of work. I gotta just love to know if he has any weightlifters or even just athletes who've done lifted some weights on occasion in his class and how they would respond to this.
so therefore, he's not doing work, even though it's extremely hard to do, but that's how we define work.
Love it.
All right.
That was great.
So for all you office people right there. All right. And so now let's talk about what if we apply.
All right, I'm just gonna stop there. I think. How long is it? Yeah, pretty long already. This is really, really interesting. I've loved, he's recognizing the difficulty of all of these vocabulary words, especially compared to the experience that students have with some of these words, right? The word work is meaningful in our culture and our society. And in physics, it has a very particular definition. I mean, what it reminds me of is take momentum and energy, right? We know that momentum and energy are very different things. One's a vector, one's not. I would claim that energy is just an accounting tool to keep track of all of these momentum swaps. That momentum is real and energy is just this weirdo made up thing that humans invented. I'm guessing some of you have a problem with that. Happy to debate that with you if you'd ever like. But think about how momentum and energy are used in sort of non-scientific speak, right? In fact, those two words are synonymous. Well, let's keep our momentum going here. Let's have some good energy here. Let's see if we can get some momentum to solve this problem. Let's see if we can find the energy to solve this problem, right? In fact, I notice it. So I'm in a lot of meetings with people. I actually kind of make note of when people use momentum and energy, and they're totally synonymous. And so we have this problem that not all sciences have. So take, for example, biology, right? Biology names these critters in all these weird ways and all of the parts of the cell. Very rarely do they run into a problem with a word that is used a lot. I mean, hey, if you're a biology teacher, tell me if I'm wrong. One example I can think of is the nucleus, right? So nucleus of a cell and nucleus of an atom are very, very different. So there's a problem. But in chemistry, if you're talking about the names of the elements, you're not really, it's not a problem. Now, how those elements interact with each other and the verbs we use for that, bonds, for example, has a meaning in society. But in physics, we kind of use all of these words that people have heard before, have used before, and yet we find new definitions for. So I really appreciate what he's done to kind of prep the students for this and to make them realize, you guys, okay, come on, this is just what we mean. This is this definition that's going to be useful to us, but recognize that it's going to be a little bit different than what we're used to. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.